Hey y'all, this is a lesson about right triangles where we talk about the Pythagorean theorem. The Pythagorean theorem only applies to right triangles. So we're going to look at a right triangle here and label the parts. So if you remember from geometry, when you have a right triangle, we've got the vertices A, B, and C, and then the sides opposite of the angles is how you label the side. So lowercase a is this side right here, BC. And then lowercase c is across from angle C, and that represents this side right here. And then side B is across from angle B, and that represents this side here. And then you can see this is a little square, and that means that it is a right triangle. So we call these sides A and B, we call both of those legs. A is a leg and B is a leg. And then C, the side across from the right angle, is the longest side, and we call that the hypotenuse. This leads us to probably the easiest formula you'll ever have to remember, and that is the Pythagorean theorem. A squared plus B squared equals C squared. So if you need to find a missing side of a right triangle, this is the formula you're going to use. Or if you need to figure out if a triangle is a right triangle, plug it into this formula, and if it checks out, it's right. So Pythagorean triples are sets of whole numbers for which the Pythagorean theorem holds true. So an example of a well-known triple is a 3, 4, 5. So if you plug in 3, 4, 5 into a squared plus b squared equals c squared, then it checks out to be a true statement, and that's a right triangle. I do want to point out, I think I forgot to mention this. A and B are the legs. Actually, never mind. Sorry. Okay, so we're going to look at these two examples, determine if the following triples are Pythagorean triples. So let's plug both of these into the formula. I'll do the first one with you, and then you can try the second one on your own. We're plugging it into a squared plus b squared, and we're trying to see if it equals c squared. I'm going to put a question mark because I'm not sure. And this is what I was going to say earlier where I got tripped up. It doesn't really matter which is A, which is B. Typically, I just start with the smaller number here. They're both legs, so it doesn't matter where it goes. But the longest side will always be the C value. So just make sure that that longest side, the largest side, goes there. And then you can plug this in your calculator if you want to. You don't have to do this by hand. We have 7 squared plus 24 squared. That is 625. And I want to see if that equals 25 squared. And it does. So yes, this is a Pythagorean triple. Now do that same thing with the next example. Pause it, try it, and come back. So in this one, we get an untrue statement. 3257 does not equal 3249. So this is no, that's not a Pythagorean triple. Then we have a couple examples of finding the missing side using the Pythagorean theorem. These are right triangles. They have the little square right there, or it'll tell you these are right triangles, but that's kind of how you know. And then we're trying to find the missing side. So in this first example, you have to first figure out what you were given. And it looks like here that the side across from the right angle is missing, the hypotenuse. So that's side C, which means that we were given A and B. So we do 8 squared plus 15 squared equals C squared. And we don't know C, we're trying to find it. And then you can add the two squares. 8 squared plus 15 squared is 289 equals C squared. And so we're trying to figure out something squared equals 289. So to undo that, we're going to square root both sides. Typically, technically, when you square root both sides of an equation, you have to consider plus or minus. But in this case, since we're talking about the length of a side of a triangle, we're going to ignore the negative case because that doesn't really make sense. And so you do second x squared to pull up that square root. There we go. 289, and we get 17. So our hypotenuse is 17 units. The next one, I want you to go ahead and set it up. I know you might get tripped up with the square roots, but go ahead and set it up and then we'll go over it from there. In this example, we're missing a leg. So X is representing a leg, either A or B, doesn't matter. And we were given the hypotenuse. So when you set up your equation, you're going to have A squared plus B squared equals C squared, and then just plug in your values. So 5 root 7 squared might trip you up a little bit, but I don't want you to worry about that. You can either type it in the calculator or do it mentally. So basically what happens here is we're squaring the 5 and we're squaring the square root 7. And so what happens, we get 25, and then squaring a square root, they're inverse operations, so that 7 just kind of pops out. And we get 175, I believe. Let me make sure. Yes, 175. Or if that freaks you out, you can do 5 square root 7. Make sure you close that parentheses around the whole number. Squared. And there's that 175. And then we have our plus x squared equals, let's see, 25 times 13, 325. Now go ahead and finish the problem. Pause it, finish the problem, come back and check your work. You should get down to square root 150. This comes from subtracting 175 from both sides and then taking the square root. Now, if you type in the square root of 150, we get 12.25 if we were to round that. You have to be careful. I don't think I specified in this example if it wants an exact solution or an approximated solution. If it wants an approximate solution, then 12.25 is perfect. But if it wants an exact solution, then we're going to have to simplify the square root. So I want to kind of go into that a little bit because this might be coming up regularly. Change this color. Here we go. So we have square root 150. You can do this several ways. You can use prime factorization or you can use perfect squares. I like to use perfect squares. I'm pretty sure 150 is divisible by 25. So it is. So it breaks up into 25 times 6. And then that breaks up into square root 25, square root 6. Square root of 25 is 5. 6 is not prime, but it can only break up into 2 times 3. And neither of those are perfect squares, so it's not going to simplify any further. So 5 root 6 would be square root 150 completely simplified. And we can type that in just to make sure. 5 root 6 should be 12.25. And it is, so I know I've done it correctly. So I can go over here. I'm going to go ahead and write my solution as an exact solution just because the original sides were given as square roots. So I kind of want my answer to match that. And that's going to be 5 square root 6. And that's it. So that's 2 examples, one where you have to find the hypotenuse and one where you have to find a leg. When you have to find a leg, you have to do a little bit of solving, but it's very basic algebra and it shouldn't trip you up too much. And then we have the converse of the Pythagorean theorem. The converse is basically using the sides to determine whether a triangle is right, acute, or obtuse. And we're going to do some exploring here to come to the converse of the Pythagorean theorem. So there's 3 statements that we're going to come up with after we kind of explore this. We have an acute triangle with side lengths 5, 6, and 7. It's not a right triangle, but I'm going to plug it into the Pythagorean theorem to explore the relationship between these sides. So if I do 5 squared plus 6 squared I'm going to do a circle right here because I'm not sure about the relationship. And 7 squared. 5 squared is 25. Let me just do this here so I don't make little mistakes. I hate making little mistakes. 5 squared plus 6 squared is 61, and 7 squared is 49. So if I were to use an inequality or an equal sign to describe this relationship, 61 is greater than 49. So a squared plus b squared is greater than c squared. So for acute triangles, if you're trying to determine what type of triangle it is, if you come up with this relationship, a squared plus b squared is greater than c squared, then it is an acute triangle. Obtuse, these are sides of an obtuse triangle. And you could probably guess the relationship here based on what we just found. But we're going to do 5 squared plus 10 squared and 14 squared, I believe, is 196, but I just want to make sure. Yep. 125 is less than 196. So for obtuse triangles, the relationship is a squared plus b squared is less than c squared. And then we already know the right triangle, but we'll go ahead and fill in the notes here. 37 squared, 12 squared plus 35 squared, and then 37 squared, and they are equal. All right, that is all I have for the Pythagorean theorem on this lesson. I hope you enjoyed the lesson. If you have any questions, please let me know. I'd be happy to help, and I'll see you in the next one.